Hello everyone. From now on, I will try to solve a few of the problems that you have requested. For the courses that I teach, if you have sent me some problems that you found challenging, I'll try to select a few of them as much as my time allows and solve them and explain them. So hopefully it helps you better understand the topics that you're learning. In this video and the next couple of videos, I will solve a few problems you have sent me for statics. So let's get to the first problem. So here you are suspending a weight W with two identical cables, where the dimension B is fixed. The span between the two fixed points is 2B, that's fixed. What you can control is H, the vertical suspension. And the goal is to select H such that the cost of the cables is minimum, right? So how do we approach this problem? So this is a statics plus really optimization. The first thing is you have to determine your cost function. So your control variable here is H, but your cost function is the cost of the wires, and it is based on the volume of the material. So if you consider length of each cable L, L is equal to what? Square root of B squared plus H squared. And if you consider the cross section of the cable A, then A times B squared plus H squared under square root is the volume of each cable, right? And you can multiply it by any constant, which is the price per volume, right? So we can consider K here to be cost per volume. And if you multiply that by a 2, of course, because there are two cables, this is going to be the total cost C. Okay, so 2 because I have two wires, and K is the cost per volume, right? So I can write it for you down. This is the cost per volume. Here, it has not mentioned that, but you can consider it to be a constant. The other thing that you have is, it says, if the tension in each rope is T and the cross section is A, right? The ratio of T to A should stay at a constant number of sigma. So you have a constraint here, and that is T over A should stay at sigma, and it should be what? Constant. Or if you basically rewrite it, you can say A equals what? A equals T over sigma. And now your sigma is constant. What is sigma here? Sigma is tension per cross section, right? Which, as you know, this is the stress in the rope, right? This is the force, this is the cross section. When you divide, you might not know solid mechanics yet because you are in statics course, but in your next course you will see strength of material or solid mechanics, and this is the stress, what we call normal stress in the rope, and it should not exceed so much of value, because if it does, the rope is gonna what? It is gonna fail, right? It is gonna break. So this constant here that you see, it says it's constant. This constant has to be what we call the yield strength of the material divided by a safety factor. So if you chose already the material for the wire, it has a specific strength and you need some safety factor. So if the cable is not perfect, or anything goes wrong, or the weight is a little bit more than what it is, or any uncertainty in the design or the application comes, the cables don't fail. Okay, so this is what we call the safety factor. and this guy is what we call the yield strength. Right? So, of course, this is a very simplified analysis, but it should be good enough for now. So you see, this is your cost function. And this guy here is your what? Your constraint. What is your control variable? It is h. So I'm writing it in terms of optimization. Now, if you remember, I said if you want to have an optimization problem, please watch my video, the first video on optimization terminologies. You need the control variable or variables to act in two different ways. In one way, they try to help with the cost function or increase it. In the other way, they try to decrease it, okay? So you might say, well, the way it looks like, h, the bigger the h is, the bigger the length of the wire is going to be, the bigger the amount of wires that you use, and that means more cost. So it seems like your cost function is not really showing a minimum or maximum, or h is just affecting your cost function in one way. It's kind of monotonously increasing. So then how can a bigger h might cause the cost function to go down? Because clearly I can see how it makes it go up by increasing the length. By the way, this p is also constant, okay? So this is a constant in the design. Well, what's the other effect of h? Well, the other effect comes from affecting a. h is going to affect a. Really? Yes. If you see here, a is t over sigma. Sigma is constant here, so a depends on t. If t gets smaller, a would get smaller. And now, is h going to affect t? Sure. This is where the statics comes in. So in order to determine that relation, we need to draw the free body diagram of the weight. So this is the weight. And if I draw the free body diagram of this guy, I have a W, and then I have two tensions, T and T. And let me call the angle that each one has with horizontal axis, let me call it theta. So theta is this angle here. Okay, if I use the traditional XY coordinate, here the problem is completely planar. And if I write the equation along the y direction, sum of the forces along y is equal to 2 times t times sine theta minus w. This has to be equal to 0. Sum of the force in the x is clearly 0 because one of them is positive t cosine theta, the other one is negative t cosine theta. So there is already equilibrium along x-axis, no worries. The only thing is here t, as you can see, is determined from w and theta. T is going to be w over 2 times sine theta. And now the thing is, theta or sine of theta does depend on h. Why? Because if I go and look here, I have a triangle. Right? You clearly see I have a triangle. This side of it is h, this side of it is b, this is theta. So sine of theta is going to be h over the hypotenuse, which if you remember, it was h squared plus b squared under the square root. So if I write for sine of theta in terms of h, it is going to be w over 2 times h over square root of b squared plus h squared. So if I do the simplification, I will get this kind of function. So now the question is this. With this kind of function that I have, what's going to happen to t when I change h? When I make h bigger and bigger, what's going to happen? Well, here your w is constant, okay? So the only thing that is variable is the sine of theta, which is this term. And when h increases, the sine of theta would increase because h is in front of theta, not adjacent to it. So increasing h will make sine theta go up, right? So as h goes up, the sine theta goes up, and it makes t goes down. And when t goes down, if you look here, because sigma is constant, t goes down means a goes down. And when a goes down, that means the cost can go down. On the other hand, when h goes up, this length of the rope goes up. So you see h has two different effects on the cost function. It makes the length of the wire be bigger, but it also makes the required cross-section of the wire to be less. Why? Because the bigger you make h, these wires are going to be more vertical like this instead of this. So their sine components gets bigger, and it's the sine component that opposes w. So the bigger sine you use, the smaller t you need, and the smaller t, the smaller tension on the rope, will require a smaller cross-section if we want to not exceed the strength of the wire and break it, right? So you are using more of the tension of the rope to keep it in place. So you see there are two different effects, and here I also to show you exactly the effect of h on the sine function. Here I wrote a very fast simple code. Here I'm using three different values of b. One is 1, the other one is less than 1, the other one is more than 1. I'm changing h in a range, and I'm plotting all three versions so you can see that the effect is definitely what I said. H gets bigger, the sine of theta gets bigger, and you see it does not really depend on b. Of course, the way it increases depends, but the behavior of all of them is monotonously increasing, okay? So the choice of b is not really going to affect the overall behavior. So now it is very clear why this is an optimization problem. And the cost function, the control variable, the constraint, everything is clear, right? So now what I need to do is I combine this equation 1 here, if you don't mind, or let me call this one 1, this one I call 2. And this guy here, this final value for t, right? This guy I would call equation number 3. So if I plug in 3 into 2, then I can find a directly as a function of h, and then what I can do is plug the result of that into 1. Okay, so let's do that. 3 and 2 into 1, that gives me my cost function directly as the function of the variable h. It is going to be 2 times k times this guy here that you can see, w over 2th, the square root term, right? and then times the other square root. So this guy here is A in the first parenthesis, this guy. And now if I simplify, remember that K is a constant, W is a constant, T is a constant, right? The only variable is H, so I can combine, and these two twos would cancel. So I can combine all these three constants into a new constant, call it K prime. And the function I will have is going to be b squared plus h squared over h, right? These two, the square root and the power 2 would cancel. So this is my cost function. I could easily replace. And now all I need is to take derivative of c with respect to h. It's a ratio. And by the way, this k prime has no effect in the derivative. We can just bring it out. It's going to be the derivative of numerator, which is 2h times denominator, minus the derivative of denominator, which is 1 times numerator, divided by denominator squared. This has to be 0 as the stationary point. And if you look here, the numerator has to be 0. This is 2h squared minus h squared minus b squared. So this is going to be h squared minus b squared is equal to 0. And that means h has to be equal to b. Okay, so if you want to minimize the cost, you better select h to be the same as b, or the theta to be 45 degrees. Right, so if you select it to be 45 degrees, that is the minimum cost of the cable that will do the job without violating anything else. You see, so we used what we learned in statics, what we learned in optimization to solve this simple engineering task, which is what vertical suspension size you would use to minimize the cost for the weight. Okay, so this is the first problem that we solved. In the next couple of videos, I'm going to go over some 3D problems of equilibrium. Thank you.